This is the demo video of our CVPR highlight paper. Our paper is named as discoscene, spatially disentangled generative radiance fields for controllable 3D-aware scene synthesis. This work is joint done with Menglay, Zifan, Saida, and other talent researchers. This paper aims at building a 3D scene generative models for compositional scene synthesis. Our framework employs a highly abstract object-level representation, specifically 3D bounding boxes without semantic annotation, as the scene layout prior for 3D-aware scene synthesis. Conditioned by the layout prior, our spatially disentangled generative radiance fields generate individual objects and the background. Our efficient neural rendering pipeline then composites the scene into a low-resolution feature map using the volume renderer, which is then upsampled to the final high-resolution image using a StyleGAN2-like upsampler. During inference, users can manipulate the layout to control the generation of a specific scene at the object level. This is a high-level summary of our approach. e.g. 3D and 3DGP have demonstrated the ability to synthesize photorealistic images with good geometry for both well-curated and in-the-wild objects. Object-centric methods struggle with scene images because scenes consist of multiple objects with non-trivial layouts and complex backgrounds. Moreover, in addition to generating scenes, we also need to maintain control over each object, such as changing its pose, shape, scale, and other intrinsic properties. So how to scale up 3D GAN to complex scenes? To address these challenges, the scene representation plays a critical role in the design process. Imagine that given an empty apartment and a furniture catalog, how should we arrange the space? Obviously, we won't throw things here and there and instead figure out an overall layout and then attend to each location for the detailed selection. From this perspective, we should leverage a layout prior because it describes the arrangement of each furniture in the space and substantially simplify the scene composition process. There exist many representations for layout, like the popular choice of scene graph, where objects and their relations are denoted as nodes and edges. Although graph can describe a scene in rich details, its structure is hard to process and the annotation is laborious to obtain in our case. Therefore, we opt to represent the scene layout in a much simplified manner, a set of bounding boxes, without category annotation. This layout prior is more friendly to collect and easier to edit, allowing for versatile, interactive user control. The introduction of the layout prior, the modeling of objects and backgrounds, becomes crucial. To model objects, we use neural radiance fields. First, we align the objects into canonical space and then use generative neural radiance fields to infer their density and color. The latent code is injected to create stochasticity, enabling weight sharing for different objects and reducing computation costs. The background is also modeled with neural radiance fields, but unlike objects, it is evaluated in world space. Here I will show how to efficiently compositing and rendering the whole scene. To efficiently composite and render the whole scene, we use a technique called ray-box intersection to adaptively calculate depth and sample only within each bounding box. This approach significantly reduces computational overhead when rendering multiple radiance fields. For bounded indoor backgrounds, such as 3D Front and Clever, we use fixed depth sampling, while for unbounded outdoor scenes, we inherit the inverse parametrization of NeRF++. When performing volume rendering on objects, we sort depth to process mutual occlusion and use alpha blending to composite object and background maps via the alpha parameter of the last points in foreground objects, assuming that objects are always in front of the background. Our framework includes two discriminators for GAN training. A scene discriminator is used to supervise the whole scene image to ensure global coherence. However, with scene-level supervision alone, we often observe entanglement between objects and the background, with the background generator learning from foreground objects. To address this issue, we project the 3D layout prior into 2D space and crop entire images into object patches. A new object discriminator, called local global discrimination, is used for object-level discrimination. This approach improves object fidelity and disentangles objects from the background. We first show the quantitative results. As shown in the table, discoscene consistently outperforms baselines with significant improvement on all datasets. With comparable training and testing cost, it even achieves similar level of image quality with StyleGAN2. We also evaluate explicit camera control on Clever and 3D Front. Obviously, our discoscene can synthesize very smooth and multi-view consistency video across different camera pose. Then we also evaluate our methods with various object manipulation applications in different datasets. Firstly is object arrangement. We can manipulate the object pose and location successfully. Even in challenging Waymo dataset, the cars are still disentangled well from background and the object consistency are kept well when performing translation and rotation. Besides, we can also update the layout by removing or cloning bounding boxes to achieve object removal and insertion. For object removal, our method can remove objects with the background and painted realistically, even without training on any pure background. It suggests for the powerful generative modeling of our model. We compare with EG3D on explicit camera control. It seems like the results produced by EG3D are very flat, resulting in consistent video. But our methods achieves better camera control. We also compare with Giraffe on object editing. Giraffe struggles to generate realistic results even in clever dataset. When manipulating objects, their geometry and appearance are not preserved well. But in our method, wherever the object is placed and how the rotation is carried out, our synthesized objects are much better and consistent than Giraffe, particularly on Waymo dataset. Besides, after training, the well-learned discoscene can also be used for real scene editing. Given real scene images, we first perform gone inversion to reconstruct them well, and then you can perform editing in your interested object like rotation and translation. Besides, we can also insert the new objects by cloning. If you don't like object, you can remove all of them and only keep background. Thanks for listening. This is all of our work. If you're interested in our paper, please come to our poster session for more discussion. Thanks again.